seconds or so, which used to take around 60 seconds or so for sorry, I'll just quit this. Mouse is not visible. Yeah. So we had tape drives which used to take around 50 seconds to access data. Then we had hard disk drives which used to take around milliseconds. So we became 1,000 times faster when it came to accessing storage through hard disk drives. And finally, we had solid state drives, which are again around 100 times faster than hard disks to and allowed you to access your data with lower and lower latencies. One common thing across all these storage devices, however, is that they are block addressable. And what I mean by that is, for these devices, accessing data sequentially is much more efficient than accessing it in a random manner. And because of that, whenever you try to access even 1 byte of the storage device, the hardware actually gives you a sector, which is around 512 bytes or 4 kilobytes of data. So we call these devices block addressable devices because of their slow random access nature. Okay, but in the last few years, since when I started PhD, there has been a new, like a revolutionary change in storage devices, and it has come through something called byte-addressable storage. Companies working on byte-addressable storage are Samsung, Intel, and so on. And this form of storage is actually 1,000 times faster than even SSDs. So now we come into nanosecond level latency of accessing your storage or storing your data. And secondly, an important property of these storage devices is that they are byte-addressable. So you can access this, even a single byte of the storage in a random access manner, because random access performance is similar or just slightly slower than sequential access performance. And we call these storage devices persistent memory, and this will be the focus of my talk. Okay. So first, let's start with what companies are actually working on persistent memory. From the hardware side, in coming up with these new storage technologies, we have Samsung, which are coming up with memory semantic SSDs, or Micron or Intel, which came up with a product called Optane. From the software side, in terms of how you can best use this storage technology, you have big companies like Microsoft and Google with their data centers, and they try to use this storage technology to its fullest. Okay. So let's talk a bit about the characteristics of persistent memory. Okay. Persistent memory is persistent, which means it is non-volatile or it is a storage device. And secondly, it is fast. And I'll explain what I mean by fast. Consider this very simplified version of a server where you have CPU, and each of your CPU cores contains its own memory called L1 cache. And there is another level of CPU cache called last level cache shared between the CPU cores. And then after that, you have the memory bus connected to DRAM and the IO bus connected to your secondary storage devices such as hard disks or SSDs. This is what a very simplified server would look like today. Okay. In the bottom, I have this spectrum of different technologies, memory and storage technologies. On the left end of the spectrum, we have the faster devices, which are in red, and here red means volatile memory. And as you go to the right, your storage becomes cheaper and cheaper, but it becomes slower and slower. And you also get properties of non-volatility in hard disks and SSDs. Okay, so to the left end of the spectrum, we have the L1 cache. And accessing the L1 cache is really fast. It takes less than a single nanosecond to access your data in the L1 cache. However, it is extremely costly, and you have to just like few megabytes of your L1 cache, maximum around 32 kilobytes actually in modern servers of L1 cache. Then to the right of that, we have DRAM, which has access latency of around 100 nanoseconds. Again, data in L1 cache and DRAM is volatile. So if you lose your power, you lose your data in DRAM and L1 cache, but it is super fast. If we come to the right end of the spectrum, we have secondary storage devices such as SSDs and hard disks, which are much slower than these fast volatile technologies, but they are non-volatile and cheaper. They can store data across power cycles. Persistent memory actually blurs the gap between volatile memory and non-volatile storage because it is similar in latency to DRAM, 3 to 5 times slower than DRAM, but it is non-volatile. So you can store your data across power cycles. Okay, so this is why I mentioned that this kind of technology is a revolutionary technology when it comes to storage. Okay, now let's see how your servers look like in the presence of persistent memory. Okay, conventionally, you have your CPU connected to memory, which serves as a cache for your underlying slow storage devices, that is hard disks and SSDs. When it comes to persistent memory, however, because the access latency is similar to DRAM, it is placed alongside DRAM on the memory bus and is controlled with an integrated memory controller along with DRAM. So here, DRAM does not act as a cache for persistent memory. Right, you can directly access persistent memory using how you access DRAM, using malloc and then mem copies or loads and stores directly. Okay, with the introduction of persistent memory, there has been changes in the Linux kernel in the form of DACs or direct access. Again, if we come to a conventional server without persistent memory, you have your applications which access storage through a file system typically. So what these applications do is that they read or write their data. They issue read or write commands to a file system. The file system underneath the hood copies the data of the files to DRAM and then accesses application data in DRAM. So DRAM actually acts as a cache for hard disks or SSDs because they are very slow. In the background, data is flushed from DRAM to your secondary storage devices. Now, when you come to persistent memory, which is similar in latency to DRAM, what happens is when an application tries to access your data on persistent memory, it issues a read or write command to the file system, and the file system directly accesses persistent memory without going through DRAM. So your DRAM is not used as a cache at all. And there is no flushing of data from DRAM to persistent memory. Okay, any questions so far?
Good, we are good.
Okay. Okay, so now let's come to what is memory mapping on persistent memory, because this is very relevant to the talk that I will give. We have the same kind of hierarchy in the presence of persistent memory that I talked about in the last slide, where you have an application in user space, file system which lies in the kernel, and then you have persistent memory and DRAM alongside each other. When an application tries to read or write a file, when it issues a command to a file system, what happens is that there is a context switch. So you go from user space to kernel, which has its own overhead because you have to store all the data on the stack and then change the stack and then go into the kernel. So this has some overhead. Secondly, the file system does a lot of stuff for the applications, such as allocating more space if you want to allocate some space for your file, or it has to do journaling to perform crash consistency, which means if you crash and come back up, your data should still be consistent. And it has a number of indexes that it has to keep updated in order to perform decently. So a lot of work is done for reads and writes in the file system. And finally, your data is accessed on persistent memory. Okay. So all these act as overheads when it comes to persistent memory, because if your storage is in the form has latency of a few nanoseconds, all these overheads add up and the software actually becomes a bottleneck. In order to avoid this bottleneck, what was introduced, I mean, this has been for a long time, but is more relevant now, is memory mapping. And what that means is when an application tries to memory map a file, all these checks are done once in the beginning. and then the file is actually mapped into user space. What I mean by that is the application can then directly access the file using load and store instructions, which is memcopy, or just move CPU instructions such as move, directly on persistent memory without going through any file system, without going into the kernel, and without doing any of these overheads. Okay, so for these applications too, is that they issue mmap, which is a one-time cost to map files into user space. And then data access incurs no context switch and no file system overheads. Okay, so with this background, let's look at what applications are there for persistent memory. First, we have legacy applications, which means applications that were actually built for hard disks and SSDs, but which you can just run on persistent memory using a file system. These examples of these applications are databases like MongoDB, key value stores like WiredTiger or SQLite, and so on. Then we have new applications for persistent memory, which are actually written for this new media using memory mapping that I explained in the previous slide. Examples of this is our Memhive, which is a startup which converts Postgres into byte-addressable media-friendly database. Then you have PMDK, which is a library that is built by Intel, which allows you to create data structures on persistent memory. Then Memcached, which is a popular caching key value store by Facebook, also uses persistent memory optionally, and so on. Okay, so finally, in today's age, because like we are in the age of data explosion, where if you see every year, the data produced and consumed is increasing exponentially. And in 2021, according to the Cisco Global Cloud Index, we actually ended up producing and consuming more than 400 exabytes of data in that year, right? And because of this data explosion, modern persistent memory applications are becoming increasingly data intensive, which means that they have very large data sets that they have to deal with. Okay, with this background, I arrive again to my dissertation statement, which is transparently achieving high performance for applications on persistent memory.
Hey, Rohan, I'll just interrupt you quickly. So actually, I wanted to understand whether the persistent memory is only accessible through mmap or a normal, through the VFS layer or through the, normal conventional layer is also possible. And do we need kernel changes for it? Maybe you are, 2-3 slides back, you have that diagram where you also talked about, here. Yeah.
So yes, you can, good question. So you can access persistent memory conventionally like any other storage media without any kernel changes. Okay. So accessing that medium is not a problem or does not require any changes. But what requires changes is efficiently accessing that medium. Because it is super fast, there are things like DACs, which come with the modern Linux kernel versions, and you don't have to do anything, but you have to run just a modern kernel in order to support things like DACs on persistent memory. Okay. But everything is relevant in terms of VFS and everything.
I see. Okay, thanks.
Yeah. All right, so transparently achieving high performance for applications on persistent memory. In the duration of my PhD, I worked on different classes of applications that access persistent memory. First is legacy applications that access persistent memory in a similar way to how they access hard disks and SSDs, which we call POSIX system call applications or legacy applications. Second is memory mapped applications, which are the modern applications which access persistent memory using mmap and loads and stores from user space to avoid file system overheads. And thirdly, the third class of applications that I looked at are data intensive applications, which are applications that deal with large data sets, which do not fit in the persistent memory of a single machine. For all these three kinds of applications, I worked on building systems, specifically SplitFS for legacy applications, WineFS for modern applications, and ScaleMem for data intensive applications. Now I'll start. This will act as the outline slide for my talk. And first I will start with how we accelerate legacy applications through SplitFS. Okay, so let's go into how legacy applications access persistent memory. Applications typically talk to a file system in the kernel, which accesses persistent memory. The way applications talk to a file system is through an API called POSIX, where they open, close files, read, write files, and so on. And there are different file systems that are built for persistent memory that implement this POSIX API. One particularly interesting file system amongst these is ext4dax. ext4dax is the modification of the ext4 file system for persistent memory. It is under active development by the ext4 community. It works with modern Linux kernel, so it is mainline in the Linux kernel. And it is the only persistent memory file system that is actually widely used today. Let us look at what overheads are, what are the overheads of ext4dax and other file systems on persistent memory. On the x-axis, we have different file systems, and on the y-axis, we have the time taken. The experiment that we are running is that we are simply trying to append 4 kilobytes of data to a file. The raw device latency taken to append 4 kilobytes of, to write 4 kilobytes of data to persistent memory is 700 nanoseconds. So this is as fast as you can get. This is the hardware limit. ext4dax, on the other hand, takes 9,000 nanoseconds in order to append 4 kilobytes of data to a file. So software overhead is the difference in the time taken by a file system to the time taken by the device in performing an operation. ext4dax has a software overhead of 12x compared to raw device latency. Similar to ext4dax, other research and file systems incur software overheads of 2.5x to 5x. So existing file systems suffer from high software overheads on persistent memory. And ext4dax, which is widely used, suffers from the highest software overhead on persistent memory. So in order to tackle this problem, the first work is called SplitFS, which is a POSIX file system aimed at reducing software overhead on persistent memory. SplitFS services data operations from user space and metadata operations from the kernel using ext4dax. So it avoids context switching for data operations. SplitFS provides strong guarantees such as atomic and synchronous data operations. SplitFS reduces the software overhead by up to 15x compared to ext4dax and improves application throughput by up to 2x compared to Nova. SplitFS is open sourced on GitHub and you can check it out. Okay, let us now discuss the high-level design of SplitFS. When you draw a spectrum of file systems for persistent memory, on the left end of the spectrum, we have file systems that are developed in the kernel, in the Linux kernel. Examples of these file systems are ext4dax, PMFS, and Nova. The problem with these file systems are that they suffer from low performance because of frequent context switching and frequent and expensive operations such as allocations and everything done on every data access. On the right end of the spectrum, we have file systems that are completely in the user space. An example of this file system is Strata. This file system, although faster than the kernel file systems, suffers from high complexity. This is because Strata has to essentially implement the entire VFS layer in the user space because it does not rely on the kernel for anything. So it suffers from complexity and bugs. We have ARI, which is partly in user space, which goes into the kernel for some small allocations, but then does everything in user space. The problem for ARI is that it is optimized for a different API, not POSIX. So you have to modify your applications, otherwise it will give low performance. And secondly, it also suffers from high complexity because of implementing the VFS in user space. SplitFS adds a new design point in this spectrum. It serves data operations from user space and metadata operations in the kernel while relying on the VFS. So splitfs achieves high performance using by accelerating data operations and low complexity by relying on ext4 DACs for metadata operations. The high performance comes from accelerating data operations from user space because data operations are typically common and simple. Reads and writes are the most common operations that are used by data intensive applications. The low complexity of ext4 comes from relying on an already mature file system, which is ext4 DACs. This is because metadata operations are typically rare and complex, and all the file system bugs that are reported are actually for metadata operations. So we rely on an already mature file system for these metadata operations. Okay, now let us look at the overview of splitfs. Consider that we have an application in user space. Splitfs, which is a file system in both user space and the kernel. So usplit is the user space component, ksplit is the kernel component, and at the bottom we have persistent memory. All reads and writes performed by the application are serviced from usplit directly from user space without going into the kernel. The metadata operations, such as creation and deletion of a file, go from usplit onto ksplit, which is ext4 DACs in the kernel, and are serviced from the kernel. Furthermore, splitfs maintains a per application log, which logs operations in order to provide stronger guarantees. So splitfs accelerates common case data operations while leveraging the maturity of ext4 DACs for metadata operations. Splitfs uses operation logging and out-of-place updates for providing strong guarantees, such as atomic and synchronous operations. Okay, now let us see how splitfs handles an interesting case, which is file appends. Now, why are file appends interesting is because appending a file typically changes the metadata of the file, such as the size of the file and so on, and it has to perform allocations in the file system. So it is fundamentally a metadata operation, but it also deals with data transfer. So this becomes an interesting case because this is a common operation that also changes the metadata. Going into the kernel for this would incur very high overheads. So let's see how splitfs handles it. When an application starts up, splitfs creates a special file of its own called staging file. Splitfs maps the staging file into user space or usplit on application startup using DACs memory mapping that I explained in the previous slides. When an application tries to append a file, that is intercepted by splitfs, and splitfs directly issues a store command, which is memcopy, from user space onto the staging file without going into the kernel and without performing any allocations for the append operation. Reading appended data similarly directly goes from this directly is serviced from user space on the staging file. Later, when an application calls fsync, splitfs introduces a new system call in ext4 called relink. What relink does is relink creates an ext4 journal transaction containing the inodes of the file foo and staging file, and logically moves the data from the staging file onto the target file of the application. Note that this is done in a journal transaction, which means this is a completely atomic operation. So it is crash safe and it does not involve any data movement. It only involves metadata transfer. So in the common case, file appends do not pass through kernel in splitfs. Okay. Apart from this, splitfs uses a number of more techniques, one of which is called collection of mmaps, which provide low overhead data access through not going into the kernel for accessing data. And finally, it uses logging and out of place updates for providing strong guarantees such as atomic and synchronous operations. You can refer to my paper for these details. Because of lack of time, I've just mentioned them in this table right now. Okay, let us see how SplitFS performs now with all of its optimizations. We run all of this on a server that has persistent memory, and we compare with other file systems that are some in the user space, some in the kernel. We answer the following questions. First, does SplitFS reduce software overhead compared to other file systems? Second, how does SplitFS perform on real applications? Okay, let us look at the first question. This is the same experiment that we had talked about previously when we saw that other file systems suffer from high software overhead. SplitFS, while providing the strongest guarantees, suffers from the least software overhead of just 80% over the device bandwidth, over the device latency. The staging and relink optimization that is used to accelerate appends helps SplitFS in this case to achieve minimum software overhead. Next, we look at a real application, which is Yahoo Cloud Serving Benchmark. This is a benchmark suite created by Yahoo and is used to actually evaluate databases. In this case, we run the LevelDB key value store developed by Google on top of SplitFS. And then we run the YCSP workload and see how it performs compared to Nova, which is a research file system, which is the next best file system. On the x-axis, we have different workloads of YCSP containing different ratios of reads and writes. And on the y-axis, we have the normalized throughput with respect to Nova. As we can see in this graph, SplitFS outperforms Nova on all of the workloads by up to 2x. This is especially the write-heavy workloads benefit the most from in SplitFS because of staging and relink, as well as the split architecture of serving data operations from user space. So to conclude this part, SplitFS introduces a new architecture for building persistent memory file systems that reduces software overhead, provides strong guarantees, and leverages the widely used and mature ext4 DACs. SplitFS is published in a conference called the Symposium on Operating Systems Principles in 2019 and is open sourced on GitHub. Okay, I'm happy to take any questions that you might have about SplitFS before I move on to the next topic.
I would like to ask one question, Rohan.
Sure.
You did mention about synchronization can be handled using the transactions you introduced. You use the ext4 transaction itself. But how about multiple applications writing to the same file? Now, in this case, I think you mentioned that on fsync, that time a new transaction will be, will happen, and that's how that metadata will get stored. I hope that's how it is. So in case simultaneously, if some other application is trying to access the same file, whether it will get delayed, updated information, or how this synchronization is handled in this case.
Right. So this is actually a very nice question. And this is SplitFS actually does not optimize for applications that access shared data.
I see.
But it provides correctness. So what it does is POSIX guarantees you that on fsync, everything should be synchronized and visible. Till you issue an fsync, there is no guarantee that POSIX provides, and that hence applications cannot actually assume any guarantees until they issue an fsync.
Yes.
So what SplitFS does is every application has its own per application log, which keeps logging data for that application. If it's a shared file, it will keep logging for the shared file. And once an fsync is issued, all of these logs of the shared files are accessed, and then everything is brought to a consistent state, and all the applications then can see the data consistently.
I see. Okay.
Yeah. Okay. But that is not something that we optimize for.
Okay, got it. Thank you.
All right. So now moving ahead, we tackle the second class of applications, which are the memory mapped applications, which are modern persistent memory applications. And for this, we build a system called WineFS, for which Saurabh is also a co-author. And we see how we accelerate those applications now. Okay. Now, first we'll see how memory mapped applications access persistent memory. These applications, typically what they do is they create one or a few large files. And what they do is they issue a system called fallocate, which allocates a file on persistent memory through a persistent memory file system. Then these applications memory map the file into user space and then directly issue loads and stores from user space without going into the kernel. Okay. The first access after you memory map, the first time you access an address, what happens is page tables are set up. So virtual addresses are mapped to physical addresses on persistent memory. And also the TLB or the translation look aside buffer is updated, which contains a cache of the address translations. And all of this happens on a page fault, which happens on the first time that you access any address. Page faults and TLB misses end up going into the kernel for setting up these addresses, and actually take up to 60% time in accessing your data. So performance of memory mapped applications depends on the number of page faults and TLB misses rather than the overheads of file systems when it comes to reads and writes. No.
The 60% is after memory mapping just for mmcopy.
Yes, it is just for memcopy. Okay.
So the page fault time is even additional. Yes. To bring the, allocate those pages and then the memory copy will happen, right?
So the memory copy includes the page fault. When you do memcopy, that is when the page fault will occur, will take 60% of the time.
Okay.
Okay. So in order to solve, because these page faults take up a lot of time, what was introduced in the kernel was something called huge pages or super pages. These pages are large pages, so they are 2 megabytes or 1 gigabyte in size, which means for every 2 megabytes, you will only fault once, right? So you incur from significantly fewer page faults. So it reduces the number of page faults and TLB misses by 500x. But it poses some requirements on file systems. These requirements are that file systems have to then allocate files in aligned and contiguous 2 megabyte blocks in order to get huge pages. So these applications, which actually do not depend on the file system for performance, actually get impacted by file systems for performance. To give an example, if a file is placed on persistent memory, which is fragmented, you won't get huge pages if you map the file. If your file is contiguous, but not aligned at 2 megabyte boundaries, again, you won't get huge pages. In order to get huge pages, you have to place your file in aligned and contiguous to 2 megabyte extents. Okay. So file systems are responsible in issuing huge pages to these modern persistent memory applications. And what makes it harder is that file systems must preserve these huge pages with age. So what happens is, as a file system ages, you suffer from frequent allocations, deallocations of files, and that fragments the free space, and that makes it harder to preserve huge pages or to get these aligned and contiguous to MB extents. Let us look at the performance impact of aging on current file systems. Okay, so the workload here is very simple. We are trying to find the sequential write bandwidth by using sequential mem copies on a memory mapped file. Okay, very simple experiment. ext4 DAGs, when freshly created, has everything contiguous, everything is contiguous, aligned, and ext4 DAGs can get a bandwidth of up to 4 gigabytes per second when it is newly created for this experiment. However, as ext4 DAGs ages, especially as it gets more and more utilized, HTXT4 DAX actually decreases in performance because it is not able to get huge pages. Finally, an HTXT4 DAX file system at 90% utilization is more than 2x worse than freshly created ext4 DAX. This is the same problem caused in the Nova file system, especially for higher levels of utilization. To solve this problem, so performance of ext4 DAX and Nova drops significantly when aged.
One quick question.
Yes.
How did you simulate the aging?
Right. So in order to simulate aging, there are open source tools. One of the tools that simulates an aged file system is called geriatrics. So what it does is that it tries to run some known aging profiles, which model an aged file system by performing allocations and deallocations of files. And then it is a process that takes a few hours, and then it can mimic how a file system would perform if it is, say, 15 years old or something.
So it tries specifically to delete or to change non-aligned blocks of files.
Yeah, so, I'll just let Saurabh speak on it because he has worked on this tool a lot.
So can you use that?
Okay, 1 second. I'll just mute. I can't. I'm not able to use my mouse.
So hi. So geriatrics is a tool that actually I have developed, and what it does is it does not cause fragmentation. It meets distributions of file size, of directory depth, and relative file age. Meaning it makes sure that the older file is the percentage of the 10% oldest files are it tries to maintain what the number of 10% oldest files are and what their characteristics are. The interesting thing is it does not take fragmentation as an objective. Fragmentation is a side effect. But what we observe is that if we exercise the file system through the reads and writes according to meeting these distributions, we end up getting an aged file system that looks very close to an actually aged file system in terms of its fragmentation distribution. So Rohan will share these slides, and it will have a link of geriatrics, with the tool that we use to actually age this, if you're interested.
Okay, thank you.
Thank you. Okay, so to solve this problem of aging in file systems, I introduced WineFS, which is a huge page aware file system for persistent memory that ages gracefully, hence the name WineFS. WineFS uses a novel alignment aware allocation policy to preserve huge pages. WineFS achieves high performance for modern memory mapped applications as well as legacy POSIX applications. The WineFS design achieves high scalability and works well with multiple NUMA nodes. And moreover, most importantly, WineFS performance almost stays the same when aged, and aged WineFS actually performs better than freshly formatted Nova, which is the next best file system. WineFS is open sourced on GitHub. Okay, now I'll talk about the insights behind WineFS. The first insight is that file systems must allocate memory mapped files on aligned and contiguous extents. Current file systems such as ext4 DAX and XFS DAX preserve the contiguity of free space, but fail to preserve the alignment of free space. WineFS creates a new allocator or an alignment aware allocation policy that for allocating huge pages to these memory mapped files. To explain this policy, consider that our persistent memory partition contains some small unaligned holes and some 2 MB aligned extents. Assume that this is the state of the partition currently. WineFS builds a tree data structure on top of the unaligned holes and a linked list data structure for the 2 MB aligned extents. When you get a small allocation for that is smaller than 2 MB, WineFS assumes that it is not going to memory map the file, and hence it issues and hence it allocates a hole for this small allocation. If there is an allocation request for 2 megabytes or greater, WineFS realizes that it might be a memory map file because that is the pattern, usual pattern of memory map files, and it allocates these large allocations using the linked list of huge pages. Larger allocations that are larger than 2 megabytes are broken down into multiple 2 megabyte allocations and allocated from the huge page list. Now, if an application frees some data, say 1 megabyte of data, because that is lower than 2 megabytes, it is added to the tree and added to the tree of holes. If there is a subsequent free extent to this extent, that is merged with this new free extent. If the merging results in a 2 MB aligned extent, it is moved to the aligned extent pool, which is the linked list. This is how large, large files of memory mapped applications are placed in 2 MB aligned extents, and small files of the POSIX system call applications or the legacy applications are placed in unaligned holes. Furthermore, huge pages are aggressively reclaimed on file deallocations and are added to the huge page aware list. The second insight is that WineFS achieves high scalability while preserving this huge page aligned extent. And why these both are kind of contradictory to each other is because in other file systems such as Nova, high scalability is achieved by using a per file log. In order to achieve high parallelism, every file has its own log of operations so that there is no central locking that happens. And Nova achieves high scalability. However, the consequence of that is that it fragments free space because every file has a log in the form of a linked list that keeps fragmenting the free space. Similar is the case with Strata, which wastes aligned extents using per process log. WineFS designs a suitable on-PM layout or on-disk layout that achieves scalability, but also preserves huge pages. So to discuss the on-PM layout of WineFS, consider what WineFS does is it divides the entire partition into per CPU allocation groups. So in this case, we have 3 CPUs. So we divide the partition into 3 even sized size allocation groups. Each of this allocation group creates its own alignment aware allocator, uses its own alignment aware allocator, which is maintained in DRAM. And each of these per thread CPU allocation groups has its own journal. The insight behind this is parallelism is a consequence of CPUs and not files. So every CPU has its own journal and not every file. So WineFS uses per CPU allocation groups and journals to allow high scalability. And by doing this, WineFS contains the metadata on persistent memory and it avoids free space fragmentation that occurs in other file systems. To talk about a few other techniques of WineFS uses per CPU journaling, which means every CPU group has its own journal for crash consistency, achieving high scalability and avoiding fragmentation. And WineFS for achieving crash consistency uses a hybrid of journaling and copy on write for providing strong guarantees like data atomicity, which also help in preserving aligned extents. You can refer to the paper for details about these techniques. Okay, now let us see how WineFS evaluates compared to other file systems. We have the same setup as SplitFS, and we compare with other file systems, including SplitFS in this work. The questions we ask are, first, how does WineFS age? Second, how does WineFS perform on memory mapped applications, which are its target applications? Okay, so we run the same experiment with the same aging profile as before, and this time we run it with WineFS, and we see that the performance of WineFS stays consistently higher than 4 GB per second, even when aged, and even when it is its utilization is increased to 90%. Okay, now we run the YCSB suite, which is the same suite that we ran for SplitFS, and we compare the performance of WineFS with other file systems. WineFS performs better than all other file systems on YCSP when run on RocksDB, which is a memory mapped application when run on WineFS. Note that here WineFS performs better than SplitFS because SplitFS is actually meant for legacy applications. SplitFS provides no benefits for these applications that do not issue reads and writes to access data, but that access data using loads and stores from user space. WineFS suffers from 30x fewer page faults compared to Nova across these YCSP workloads. So to conclude my second part, WineFS demonstrates that it is possible to design a file system that achieves high performance for memory mapped applications, high scalability for POSIX system call applications, and maintains this high performance in the presence of aging and under high utilization. WineFS was published in SOSP 2021, so 2 years later than SplitFS, and is open sourced on GitHub. Any questions about WineFS?
Go ahead, Philip.
So you consider WineFS a successor to SplitFS, or are there areas where SplitFS still performs better than WineFS?
Yeah, thank you for this question. So these are actually complementary systems in my opinion.
Okay.
SplitFS targets legacy applications which don't do memory mappings and accelerates them, whereas WineFS is more targeted towards newer applications. So they can work in conjunction with each other to provide probably a file system that is good for both, but that would require some kind of redesigning. But yeah, I look at them as complementary.
So I have a question regarding what kind of workload have you run while taking those numbers? I believe with combination of small IO and large IO, you may come across a scenario where it may get a little bit fragmented, because in case of WineFS, you see that for the small allocation, you have that tree, and for large allocation, 2M, you have the linked list. And you move around those chunks between these two systems, right? Smaller allocation and the bigger allocation. So if you come across a really random workload where, these small and large IOs are happening, you keep on moving the chunks around and may get some kind of, imbalance as well between these two systems, or maybe an overhead. Just a question, or how the WineFS handles it.
Right. So if we go back here, if you look at the aged setup here, this is actually what I mean by aged is there were some small allocations that happened in the file system. And then I ran a workload which tried to do large allocations.
Right.
So 90% thing actually kind of imitates what you were mentioning, right?
Mm-hmm.
And in this case, like what we see is that the performance of WineFS stays high. And what I mean by moving these things around is it's just an in-memory tree and a linked list. So what I have to do is simply remove an element from a tree, add it to a linked list.
Pointers, you
Involve
don't
any
move it.
transfer of data or anything.
Correct. Got it. But it may happen. Is it like it may happen that you have a already completely utilized small memory tree, and now you wanted to allocate more, and then you have to then go back to the system and then that time move the pointer to the small tree, then from the linked list, something like that.
Right. So WineFS actually advocates for a proactive approach to not reach this state in the first place where you have just holes in your file system. Okay. But again, it might be possible because if you only run if you only have small files throughout and never issue large files, you can end up in a state with holes in your file system. And in such a rare occasion, I would advocate using some defragmentation tool that brings your file system to a nice state, and then you can run your workloads. But as far as possible for real world setups, we proactively try to avoid creating holes rather than doing defragmentation later.
Also, the per core data structures, because they are per core, they tend to be not as heavy and mismanaged as a global data center would, like a bitmap, like a global file system level, a tree or file system level links.
Right.
And because they are core code, you can imagine if you start your application on another code, or if the application gets transferred to another code, the data structure might be much more better suited, and you might not reach that problem.
Yeah.
You're seeing.
Okay.
That is also possible.
Okay. Good.
But do you assume that these applications are then pinned to those cores?
So that is some possible future solution. Currently, we don't actually do this, but a solution of when you might have your file system fragmented is to maybe pin applications to different cores.
Mm-hmm.
Yeah, actually, I was also thinking about the same. Is it like if you wanted to then access those specific inodes or file data, which is basically in a section which is for that particular CPU, you always redirect the request for that particular core or CPU in that case. So
Right.
as CPU,
there might be some imbalance in the CPU load.
correct.
Right. That is a possibility.
That's true, but you are talking about high-end data center level or high-end servers, where you would expect on average that the core utilization is balanced. Otherwise, even with or without YNFS, if you have imbalance in how your cores are being used anyway, you are going to have some hotspotting, which is going to be difficult.
Okay.
But you also have to have some kind of overarching data structure, right? That maps to these cores. So you actually have a fully consistent tree in the end.
Yes.
Yes.
Yeah, you need some kind of more load, global load balancing kind of thing.
But I think what Philip was saying is that today, can you make sure that your tree at the global level is fully consistent? It is.
Yes.
Right? There is no sharing of inodes between across cores.
No.
So you only have an inode either in one core or the other, and therefore it's never the case where you might have broken data access or metadata line.
Yeah, and to elaborate on that a bit, it is not necessary that a file be in the allocation group of a single core itself. You can have a part of a file in one group, and then if there is a thread migration and if some other thread tries to access that file, the other data of that file will be in some other core. As long as it is 2 MB aligned and contiguous, it doesn't matter where it is. So there might be multiple opportunities to get some load balancing and not impact performance negatively.
Okay.
You might want to ask whether you want to do third party.
Yeah. So yeah, we are actually out of time. I have one more project that I can explain, but I'm happy to stop here if we are constrained on time. Or people can log out if they have to go, and I can continue. So whatever works.
Yes. I think we can continue. If somebody has some time constraint, maybe they can drop out then.
Okay, but yeah, please keep asking questions. I'm really enjoying this talk. Okay, so now talking about the third work, which is currently under submission. It is in this third work, we built a system called ScaleVim, which actually targets data-intensive applications, which means applications that do not fit in the persistent memory of a single server. Okay, so data-intensive applications are modern persistent memory applications. So they issue loads and stores from user space without going through a file system, but just that their data does not fit in the free space of a single persistent memory server. These applications typically create one or a few very large files using something, so they can allocate files using fallocate, similar to the YNFS case. They talk to a distributed persistent memory manager, which decides where to place which parts of the file across the servers. Then these applications map the file in the user space, and then they issue memcop. They issue loads and stores. The loads and stores issued to the local part of the file can go through without any problems, but the loads and stores to the remote parts of the files involve data migration from a remote node to the local node in order to get serviced using native loads and stores. Okay, makes sense. So data intensive persistent memory applications comprise of single node applications. So this application itself is running on a single server, but it just has very large data. So single node applications with large data sets. Secondly, distributed persistent memory managers are NFS, which is a distributed file system, or hotpot, which is a distributed shared memory system. These systems typically manage this data across multiple servers. Let us now look at what are the properties of data intensive applications that they expect from these distributed persistent memory managers. The first property is they should support native loads and stores for their data, because these applications do not want modifications. Say you have a key value store like RocksDB. You don't want to change RocksDB in order to just store data across, just have a large data set. This is the happy case where both the current kinds of systems support native loads and stores. Second, do they support DAX, which means that in DAX, if you remember, there is no copy of data in DRAM. You directly access persistent memory. So everything is synchronous and there is no flushing. Do current systems support DAX? The answer is no for both. Both these systems have to copy data into DRAM and then service it from DRAM, and cannot use DAX or do not provide correctness when you use DAX. Third, do they support memory mapping of files that do not fit in a single node? Answer is no for both. Both of them require that the entire file be present in one of the servers, not both. But they can support an application with multiple files across multiple nodes, but each file should fit completely in one server. Finally, do they support large data sets? Answer is yes for NFS, because it's a distributed file system used widely today. But Hotpot, which is a more of a research prototype, does not support large data sets and requires that the entire data set fit in the persistent memory of a single node, even if it is a remote node. So existing systems are unable to support distributed DAX memory mappings. To solve this problem, I introduced ScaleMem, which enables transparent scaling of applications to the persistent memory capacity of multiple servers. ScaleMem co-designs the file system and memory management layers to support remote DAX memory mappings. ScaleMem binds to applications and provides tailored policies which are suited for particular applications to provide high performance. And ScaleMem outperforms NFS by up to 7x while providing stronger guarantees and DAX support. I will open source ScaleMem once it is published. Okay, now I'll discuss about the high-level design of ScaleMem. Consider that you have two servers that are connected to each other. Each of them has persistent memory and runs a persistent memory aware file system like WineFS. ScaleMem builds a service called Node Manager on each server, and each of these node managers monitors the free space of its local persistent memory. And these node managers communicate with each other via a fast networking protocol called RDMA, or Remote Direct Memory Access. Applications, when they start, they bind to a library called App Manager, which is also a ScaleMem library, which contains application-specific policies for tracking data accesses of the application. The App Manager, after tracking the data accesses, communicates with the node manager using shared memory. So Application Manager binds to applications to provide application-tailored policies and hot data tracking. Node Manager implements the mechanisms to migrate the data according to the instructions given by the App Manager. Okay, so with this high-level design, let us go through the data access path quickly in ScaleMem. Consider that you have two servers, each with 50 GB space, and then you are in a state where you have a single file of 100 GB, where half of the file is in server 1, half of the file is in server 2. You start an application on server 1, which binds to App Manager in server 1. The application says that the application wants to memory map the 100 GB file. Okay, the application, note that the application is unaware of where its data is. It does not know if its data is local or remote or anything. It is just assuming that its entire data is in the local. Application tries to memory map the 100 GB file. This call is intercepted by the app manager and a mapping of the file is created in user space. Note that only the physical addresses corresponding to only the local portion of the file are actually populated. The remote portion of the file only contains virtual addresses and no physical addresses. And a consequence of this is when you try to access a virtual address without a physical address backing it, it generates a page fault. Okay, now consider that the application tries to issue a mem copy in the local portion of the file. No problem. The app manager can directly access using native loads and stores and return the result to the application without involving any application changes. Now, when an application tries to access the remote portion of the file, it generates a page fault or a remote page fault. This page fault is forwarded to the app manager from the kernel to user space using a technique called user fault FD. So app manager has a thread which keeps looking for page faults. So it comes into the page fault handler. The page fault handler fetches data from the remote node, which involves data transfer from server 2 to server 1. And if the server 1 is full, eviction from server 1 to server 2. And then after that, the application can proceed to directly access data because it is now brought into the local server. Okay. All of this is transparent to the application. For the application, it is just a mem copy that took a long time. Okay. Rest everything is underneath the hood. A remote page fault, it results in allocating a block in the local file and creating the mapping between virtual and physical address. So memory mapping the block. Similarly, an eviction ends up punching a hole in the local file and unmapping the block from the local region of the file. Okay, so these both are very expensive operations, and we will look at the cost of a page fault and eviction now. A page fault and eviction, a remote page fault and eviction involves both the memory manager and the file system. Specifically, the memory manager contains a global tree per process, which contains memory mapped regions by that process. Similarly, the file system contains the global free space allocator, which tracks free space of the file system. Okay, assume that you have a file which is 50 GB in the local node. Now, when you get a page fault for a remote region of the file, what happens is, first you have to allocate 4 kilobytes of data. That involves grabbing a global lock on the free space allocator and then finding a free 4 kilobyte region and then removing it from the free space tree. Second, fetching the data from the remote node, and which involves grabbing a lock on the file because you add the data to the file in the local node. Third, you memory map the block after that because it has to be accessed using loads and stores. So this involves grabbing a global lock on the memory manager tree in order to add a new node of 4 kilobytes in this global tree. So a remote page fault or eviction requires global locks at both the file system and the memory manager layer, and these are scalability bottlenecks fundamentally. Secondly, frequent page faults and evictions end up just transferring 4 kilobytes here and there, and what they end up doing is they end up bloating these global data structures. And so every time you hold a lock, that lock becomes more and more expensive as your file system ages or as your application keeps running due to these random evictions and page faults that happen in the runtime of the application. To alleviate these bottlenecks, we introduce a technique called fast reallocation. What this technique does is it keeps in the memory manager, in the memory mapped regions, it keeps stale pages as they are. It never deallocates or it never changes the structure of the tree. So it has a list of active pages and stale pages in its data structure. Secondly, In the file system layer, ScaleMem creates a linked list of just holes. These holes are the holes that get created during evictions, and they are not added to the tree, but rather kept in a separate linked list to not bloat the tree. So a remote page fault or an eviction, when it occurs, it has to allocate 4 kilobytes of data. So it grabs a lock, which is a global lock on the linked list of free holes. But remember that this is a very simple data structure, and it only needs to remove the head of the linked list, which is an O of 1 operation. So this lock is very cheap and independent of the number of nodes. Okay, so this happens fast. Fetching the data is the same as the previous case. Third is now you want to map that page. In order to do this, you already have stale pages in the memory manager, which you just mark as active. So you don't change the structure of the memory map region tree, which means you don't need to hold a global lock of that tree, and you can just mark those pages as active and put physical insert physical addresses for the virtual addresses. I'll just finish this. So this requires no lock, and because of this, fast reallocation avoids using of expensive locks and increases scalability. Yes.
Is the conversion of using or marking a stale page? You're saying you don't need locks because it is atomic?
No, because it does not change the structure of the tree. Removing or adding a new node into the tree requires a tree level lock.
I understand, but what if two people go to mark the same node active?
No, that you have node level locks. Yeah, that node is locked, so that is atomic, but that is not a global lock.
And if node is locked, do the children have to lock?
No, only that node.
Because it's not going to change any parent.
Correct, correct. Okay. So ScaleMem uses a few other techniques such as fine-grained read caching, which is used to accurately track hot data and avoid write amplification. And it also uses data prefetching because the application manager binds to applications and can know the data access pattern of the applications, so can prefetch data and reduce the number of page faults. The details of these are in the paper, which is under submission. Okay, now let's see how ScaleMem evaluates compared to NFS. We tried comparing it to Hotpot, but Hotpot is deprecated and it does not support, it does not run on Linux kernels anymore. And also it does not support large data sets. So we could not really evaluate it in any meaningful way. So the system that we compare to is NFS. Okay, we answer the following questions. Does ScaleMem scale with increasing number of threads due to fast reallocation? Second, how does ScaleMem perform on real-world applications? For measuring the scalability, we run a simple experiment where we sequentially read the data using mem copies such that half the data is in the local node. We do this using increasing number of threads on the x-axis, and we report the throughput in ops per second on the y-axis. In the absence of fast reallocation, these global locks are significant scalability bottlenecks, and they do not scale at all as you increase the number of threads. However, with fast reallocation, the performance of this simple experiment increases linearly as you increase the number of threads. Okay, now we run the same experiment, which is the YCSP workload suite, on two different key value stores, RocksDB and LMDB, and we measure the performance of ScaleMem compared to NFS. Here again, half of the data can reside in the local node and half is in the remote node. We evaluate our performance normalized to NFS. So NFS is at 1 in each of these. I should have added the raw numbers, but didn't add it by mistake. But assume that NFS is at 1 for all of these. ScaleMem performs up to 7x better compared to NFS on this workload. And this is because of its high scalability and because of the other techniques that it follows. One workload where ScaleMem is worse than NFS is the load A workload, which is 100% writes for RocksDB. In this case, NFS does some tricks, which means that because it's a write-only workload, it does not need to fetch from remote node, and it can just allocate a new region in the local node. But this this violates the DAX property, which is why ScaleMem has to use the remote, has to fetch a page from the remote node even for writes. Overall, ScaleMem performs up to 11x lesser network I/O because of its application tailored policies compared to NFS. So to conclude, ScaleMem is a subsystem to support distributed DAX memory mappings that allows unmodified applications to use the persistent memory of multiple servers, uses fast reallocation to reduce memory management and file system overheads, and allows fine-grained tracking and DAX of data tailored to application access patterns. This paper is under submission and I will know about it in the next couple of weeks. And after that, I will open source the code. This concludes my talk. And just to summarize, we discussed 3 different classes of applications, legacy applications, modern applications, and data intensive applications. And we discussed systems that try to tackle the overheads in each of these classes of applications to achieve high performance for persistent memory. Thank you. With that, I can take questions.
Okay, great. I have one question, Rohan. So have you thought about ScaleMem, how it could be used as a completely distributed file system, or how does it fit into, that area?
Right. So completely distributed file system involves many more things like replication and fault tolerance and things like that. And it is designed for distributed applications.
Right.
I believe that there's a lot of work that is already going on there, but this kind of application space where you have increasing data sets, you just have your applications that are running, but the only difference is that they have larger data. And today there is no system that can support an application with large data. So we try to tackle this using ScaleMem. Adding fault tolerance replication to it is an interesting future direction, but that was not the focus in this work.
Any other questions, anybody?
I had one,
Sure.
which is related to how you intercept the system calls. But because you mentioned in SplitFS, you have this user space part that everything goes through. And that's essentially a library, I assume. And that library just intercepts all the system calls, or how do you do that?
Yes, so there is a mechanism called LD preload. So it is an environment variable. If you set LD preload equal to some library, what happens is all library calls go through that library first. So we use LD preload in order to intercept all the system calls which come to our library first, and we service them from user space whenever we want to, and just pass them on to glibc or the kernel whenever we want to rely on the kernel. So that is what we use for ScaleMem as well as SplitFS. Okay, yeah, that's also how we are imagining if we're going to use a space with the file system, then this is, I think, a technique that's widely used. Right. Yeah. There is also a library by Intel called syscall intercept, which actually helps you to only implement the system calls instead of implementing the entire glibc address space. For example, if it's a write system call, in glibc you have fwrite, pwrite, vwrite, and 100 different kinds of writes, which all boil down to just one file system write call. And this syscall intercept helps you to just implement this write call, and it does the job of intercepting all of the other glibc calls so that you don't have to have implementations of each of them.
Yeah.
Oh, yeah, that's helpful. Yeah.
And Rohan, this memory manager or application manager you have implemented, right?
Yes.
So this is how you avoided application changes, like legacy applications can work on the persistent memory without any modification, right?
Exactly. Yes.
Okay. Do you know any other system where you have to change the application as well, and how they need to change it to run on persistent memory in that case?
If you are building a file system in user space, then I believe this is the only way you can run applications unmodified. Otherwise, you just have to change your applications and modify them to whatever calls your library implements. And an example for this is a library called PMDK by Intel, Persistent Memory Development Kit. It has certain interfaces for you to create data structures, but then the applications have to be modified to use them, and it becomes a little complicated then to ensure correctness.
Okay. Okay. Yeah, as it bypasses all these generic layers altogether.
Correct.
Yeah. Okay. Cool.
Another example would be GDS, for example.
Yeah.
That also requires application changes to read and write files. If you want to make use of the direct nature of that library. And they do it they do it a little bit differently, and as in they let you use their own calls for everything, and then they map that to POSIX calls if needed again. So they kind of do the other way around. You can write your whole application for GDS, and then the kernel driver decides where the stuff needs to go.
I see.
That is also an approach that you could take there.
Right. Makes sense.
So I wonder, have you heard about DAOS, which is Intel's? DAOS.
I believe that also requires application changes, and yeah. But yeah, that was something that I was looking into when developing ScaleMem. But just that we diverged in a way where we couldn't really compare it with DAOs.
Okay. Okay, great. Any other questions, anybody? No? Okay, thank you so much, Rohan. This was really, really interesting, and we learned a lot actually. And you explained it so well with all those examples, and gave different kinds of system as well that help to understand things really well. So thank you so much, and great work.
Thank you.
So if you, I don't know, Saurabh, you want to, quickly talk about your work as well, or we do it other time? That's totally up to you.
If you guys are up for it, another time would be better, because I just struck to something right now which won't make a lot of sense.
Yeah.
You already got a lot of information right now. So next time.
Sure. That sounds great. Okay. Thank you so much. Thanks for your time, Rohan.
Thank you, everyone, for listening to my talk.
All the best.
Yeah. Thank you. Great talk.
Thank you.
Thank you.
Okay. Bye-bye.
Bye.